Two system administrators, separated by 3,000 miles, hit Enter at the exact same moment. They are targeting the exact same network resource. They are each adding a distinct new user account to the exact same Active Directory group. Active Directory is the database system Windows uses to manage network permissions and resources. The network registers both inputs, but only one user actually joins the group. The second update perfectly overwrites the first, erasing the other administrator's work without triggering a single error message. This exposes the central friction in distributed systems. You have to allow geographically separated domain controllers, the servers that authenticate network users, to update a shared object simultaneously without destroying each other's data. To see how this data vanished, we are going to perform an autopsy on a legacy environment, Active Directory running on Windows 2000 server. The flaw isn't in the network cable, it is inside the database's specific handling of the group's member attribute. The member attribute is a single, multi-valued list. It is designed to hold the distinct identities of potentially thousands of individual users within a single organizational group. In Windows 2000, this architecture carried a physical constraint. Any change to that list forced the server to process the entire array of users in a single, unbreakable database transaction. Fixing this required a structural redesign of how Active Directory handled replication, an upgrade introduced in Windows Server 2003. Silent data loss on a global network is rarely a random glitch. Here, it was the predictable mathematical outcome of a monolithic database constraint, a constraint that forced engineers to invent a new mechanism called linked value replication. Inside a legacy Active Directory group object, a member attribute container locks 3,000 users into a rigid list. Adding one row requires the server to pull the entire box into memory and completely rewrite all 3,001 rows back to disk. This poses an immediate scaling problem. The underlying database engine has a strict physical ceiling for how much data it can process in a single write operation. For Active Directory, that hard limit is approximately 5,000 values per transaction. If an administrator tries to add a user to a group that already has 5,000 members, the write operation simply fails. The database rejects the update. Beyond the physical write limits, this monolithic structure creates a bottleneck at the network layer during server synchronization, leading to high bandwidth consumption. Consider what happens when an administrator adds just one single person to an existing 3,000-member group. Because the update is processed as a single monolithic block, the server is forced to transmit all 3,001 values across the network to synchronize with the other domain controllers, instead of just sending the single new addition. This illustrates lost changes during replication latency. Domain controllers 1 and 2 hold identical blocks of 3,000 members. An administrator updates controller 1, which begins transmitting a massive payload. Simultaneously, another administrator updates controller 2, transmitting its own massive payload slightly faster. These massive payloads move toward each other, meeting at a collision point. Relying on strict last writer wins logic, the system blindly accepts the newest timestamped payload and destroys the older one, completely replacing the first administrator's update. A system designed this way turns a routine administrative group update into a waste of network bandwidth and a mathematical gamble with the integrity of the directory. Solving this required a structural change to how data is handled. By upgrading to Windows Server 2003, the system adopts a completely different operating model. This new model relies on linked value replication, or LVR. LVR is an architectural mechanism that permanently decouples these previously rigid arrays into individual components. This diagram shows the new state of the member attribute under LVR. The 3,000 user rows are now individual, independent blocks. They are no longer fused together, allowing each value to replicate completely separately from the rest. Revisiting our scenario, an administrator adds a single user to a group of 3,000 members. Because the list is no longer a monolith, adding one user now only transmits that single isolated value. The massive payload overhead is eliminated. Now consider the concurrent update collision scenario, where administrators hit Enter at the exact same moment on Domain Controller 1 and Domain Controller 2. When those payloads meet in the center, LVR evaluates the simultaneous changes to the exact same group without triggering a destructive overwrite. Because the individual member values are decoupled, the system sees the additions from different servers as independent, non-conflicting events. Both administrative updates survive. They pass each other safely and merge into the centralized directory. By breaking data down to its smallest functional part, linked value replication replaces the brittle monolithic pipeline with a granular, conflict-resolving distributed system. However, this architectural upgrade does not remove the physical database transaction constraints. The limits of the local server hardware still apply. To understand why, we have to recognize the critical processing distinction between an originating update and a replicated update. This flowchart displays two distinct data paths. Path A represents an originating update, the first LDAP write made directly to a local domain controller. It must commit to the local disk immediately, bound by the single transaction physical rule. Because of this constraint, architects recommend limiting single originating writes to 5,000 updates. But Path B, the replicated update, behaves differently. Arriving over the network, LVR bypasses that single transaction bottleneck, allowing incoming data to freely split into multiple sequential transactions. Because replicated updates span multiple database transactions, massive directories with tens of thousands of users can synchronize safely in the background across the global network. Beyond safe synchronization, this decoupled architecture enables a secondary operational benefit for disaster recovery. Consider an authoritative restore, which is the process an administrator uses to recover a deleted user account from a backup and bring it back to the live network. In the legacy monolithic system, bringing that user back did not automatically restore the groups they belonged to. The administrator had to manually reassign their previous access. Under LVR, the system maintains unique backlinks for each object. These links allow the server to automatically trace and reconnect a restored user account directly to its previous group memberships. This automated recovery is only possible because each membership is now an independent, identifiable link, rather than an anonymous row buried inside a monolithic block. Understanding linked value replication reveals a necessary balance. By working within physical local database limits while maximizing distributed network efficiency, engineers turned Active Directory into a resilient enterprise-scale architecture.